whole boxcar full of these things, and you may pull out a couple of dozen of them, for example, weigh them up, and calculate the mean for the particular sample that you have. And you could calculate its standard deviation. Now, if you want to get what the problem really asks you is, how in the world would you get a better estimate of the mean of a population? And it gives you some of the things that you could pick. And guess what? One of the ones that you pick is you increase the size of your sample. That's pretty straightforward. You get a better estimate of the mean. Of course, if you really want to know the mean, you could measure every darn one of them. But usually we don't do that. Now, the functional form of a curve is given. Differentiation can be used to determine all of the following. In this particular problem, and I should put that one back up so that you can see it momentarily, it's problem number 6. And of course, going from that small type down to, or that large print down to this small type is not going to work just real well, but I hope you can follow with the materials that we have here. Notice that the concavity of the curve, yes, you can determine that by differentiation. The location of inflection points, well, of course, I can determine that by differentiation. The number of inflection points on the curve, I use differentiation to get that. But there's no way in the world I can determine the area under a curve between certain bounds by differentiating. That, of course, is a property of integration. So sometimes the answers are pretty obvious. Now, the next one they give you is a really toughie of a differential equation. It is a first-order linear differential equation with a constant coefficient and an easy initial condition. It asks you to determine y of t. I have used a little different notation than the text uses here, but basically this one gives you r plus 5 equals 0, and r is equal to minus 5, therefore. You find that y is equal to c e to the minus 5t, and you have to determine this constant. And the constant is simply obtained by putting t equal to 0 and observing that y is 1. And that shows you that c1 is 1. So what's the answer? B. This particular set of problems uses operator notation. And I don't remember that the manual does, so they have probably changed that a little bit because this exam is back from a year or so ago, and I don't think they put out a new one. The differential equation in this case is d plus 2, and I'm going to write out what the differential equation is just above that so that you can see it in its usual form. It's y double prime plus 4y prime plus 4y equals 0. Now that will give you the equation, the characteristic equation, r squared plus 4r plus 4 equals 0. And that will give you the values r equal minus 2 and minus 2. That will give you y is equal to c1 plus c2x e to the minus 2x because we have repeated roots. Let's take a look at the next one. We have rectilinear motion. Rectilinear motion, and that's interesting that they put this one in a mathematics exam, is motion along a straight line. And they are telling you that the position along that line is given by the equation 20 t cubed minus t to the 4th. They want you to calculate the rate of change of acceleration when t is 2. Acceleration itself is the second derivative. So we have to differentiate once to get ds dt, and that's 60 times t squared minus 4t cubed. The second derivative is 120t minus t cubed. The third derivative is 120 minus 24t. We now have the rate of change of acceleration as 120 minus 24t. So when t is equal to 2, the ADT will come out to be 120 minus 48, or 72. Well, that really wasn't a very difficult problem. The next one they asked that particular group was to deal with two vectors, A and B, and to determine a unit vector perpendicular to the plane of A and B. In this case, a vector perpendicular to A and B is simply the cross product of A and B. So we set up our determinant, ijk, we set up the vector A, 2, 4, 0, the vector B as 1, 1, minus 1, and we calculate the cross product A cross B. Notice that we take the minor, I, and 4 times minus 1 gives us minus 4 going that way and 0 coming back, so we get minus 4i. The j component sits in the minus minor, plus minus plus, and the determinant is 2 times minus 1 and 0 times 1. That is a minus 2, of course, but remember that's the minus location for the minor, so it is plus 2j. Finally, the k component, plus minus plus, it's sitting in a plus minor, and its determinant is 2 times 1 minus 4 times 1, and we end up with a vector A cross B minus 4i plus 2j minus 2k. Its magnitude is the square root of the sum of its squares, which happens to be 24, or 2 times the square root of 6. The unit vector is just our A cross B divided by 2 times the square root of 6, and that is one of the listed answers. Here is one that you can solve simply by reading the manual. The answer was given right in the manual. It says y is equal to a function of f of x. Determine the definition of f prime of x. Well, f prime of x is a limit as delta x approaches 0. F of x plus delta x minus f of x, all divided by delta x. That one was a gift. They were letting you save up time for a really tough one. Here's one that may take you just a little longer. We're given a curve, x is equal to y to the 3 halves. And it asks you to determine the area in the first quadrant bounded by y equals 1, the curve, and the x-axis. Let's see. I got to read this again. Determine the area in the first quadrant. First quadrant is this one. Bounded by y equals 1, the curve, and the y-axis. Okay? I draw in my little element, like this, shaded up, dy, and I set up my differential element that says dA is equal to this distance x times dy. Okay? Now x is y to the 3 halves dy. My range of integration is from y equals 0 all the way up here to y equals 1. I'll add up all of these little slices going through here. The integral from 0 to 1 of y to the 3 halves dy is going to be y to the 3 halves plus 1. That's 5 halves. Divided by 5 halves, which is the same as multiplying by 2/5. So I end up with 2/5. Upper limit is 1. 1 to the 5 halves is 1. And of course the lower limit is 0. So I end up with 2/5. Not too bad. Okay? An integration problem, but setting them up and drawing a good figure in the margin of the thing will serve you reasonably well. Now that is a set of sample problems from a morning session. And you want to remember that in the morning session, I believe it is now, you work 60 problems in the morning session in a 4-hour period. So if you have a 4-hour period, 60 times 4 is 240 minutes, and you're going to work 60 problems. That gives you about 4 minutes a problem on the average. In the afternoon, is that 60? It's 120 in the morning, isn't it? 2 minutes per problem in the morning. Because in the afternoon, you get all outdoors to work the problems. You get 4 minutes a problem to work them. So I did also pick up some that come out of an afternoon session so that you can see a little bit more about what these look like. Now, the problems look pretty much the same, but the individual natures of them will be a little different. For those of you that are following along, this is general questions, 30 questions, and these are coming out of this one. This is again from the National Council of Engineering Examiners, and it's telling us to solve these problems. I'm going to go to the solutions that I have written up because it is bigger type and it will be much easier for you to see as I explain what's going on. We are given the differential equation. In this case, the independent variable is time, t, and the dependent variable is x. And we're given the equation, the second derivative of x with respect to t plus 16x is equal to 0. And when t is equal to 0, we are given the fact that x is 0.08 meters and that dx dt is equal to 0. We are asked to determine x of t. Well, I used operator notation to solve this thing. By what you have in the book, you would use a little different form. And you would set up the characteristic equation that says that r squared plus 16 is equal to 0. And you would conclude that r is equal to plus or minus 4i. That puts you immediately into the solution x is equal to c1 cosine 4t plus c2 times the sine of 4t. You solve for the constants by putting t equal to 0 in this first one. For instance, you find out that when t is equal to 0, the cosine of 0 being 1 and the sine of 0 being 0, x of 0 is just equal to c1, which is 0.08. The first derivative, and I should point out here that this dot notation was originally developed by Newton, so it's certainly not new, but it certainly can be confusing to students if they've never seen it before. But the dot notation, x dot, is just equal to dx by dt. It's a very universal nomenclature. The first derivative of x is minus 4 c1 sine 4t plus 4 c2 cosine 4t. And we find the value of c2 by putting time equal to 0, and x of 0 comes out to be c2, and the initial condition back up here in the beginning said that when t was equal to 0, dx dt was equal to 0, so c2 vanishes. Therefore, our solution is just x of t is 0.08 times the cosine of 4t, which is answer D. The next part of this question asks you, what's the biggest amplitude of this thing? One of the unfortunate things about this little sequence of problems is if you really messed up the first one, you may mess up a second one. So sometimes the sins of our present catch up with us as well as our past. In this case, the amplitude is just the biggest value x can have. Now, if you want, you can differentiate this thing and look for the biggest value, and you will find out that its biggest value is 0.08. You can also look at this and recognize that the biggest value that a cosine has is either +1 or -1. So this thing is never going to get outside of 0.08, so its biggest value. The next one is to determine its period. Now, the period, there is a little formula which I did not see in the manual, so this one may not be game when we get into the exams now, but the formula is that when you have the cosine of 4t, that is of the form cosine of omega t. Omega is what's called the circular frequency, and it's equal to 2 pi times the frequency. So the frequency is equal to omega divided by 2 pi, and this problem asks you for the period. The period is the reciprocal of the frequency. Consequently, looking at this, the period will come up when 4 times t, I call the period big T, equals 2 pi. The cosine will repeat itself after that, and I can solve for the period as pi by 2. So you can do that either way. That was a rather nice little set of problems, but they are coupled together, and that's one of the little hazards that one has to look for in these kinds of problems. They can be put together in that way. The next page that you had in the assignment of the problems looks like this, and I'm going to go to my bigger solutions to actually work through it. You're given an equation, y is equal to 8 minus 2x squared, and at the point x equal 1, y equals 6, you're determining the equation of the line normal to that curve. Aha! Normal to the curve. The slope of the curve, y prime, is just equal to minus 4x. That comes from just differentiating this equation up here. Minus 4x is the first derivative. At the point x equal 1, y equals 6, the slope is going to be equal to minus 4. We just put x equal to 1. And that's the value of y prime for the curve. The slope of the normal is the negative reciprocal, or plus 1/4. So the slope of our normal curve, mx plus b, or the equation of our curve, mx plus b, is going to be 1/4 x plus b. Well, at x equal 1, the y value must be 6. So we can substitute in this, putting x equal 1. Look at that. I left the x in there. That should be 6 is equal to 1/4 times 1 right here, not x, plus b. So b itself is going to be 6 minus 1/4. Y then, you can put these values back in, and this one does require just a little bit of manipulation. I left the x out of here, put it up there. That's what I did. Y minus 6 is equal to 1/4 x minus 4, 1/4, and you can get it around into one of the forms that's listed. Actually, once you know that slope is plus 1/4, you can narrow it down. I'm sure that other instructors in this series have pointed out to you that there is no particular penalty for guessing. Sometimes you can look at a set of answers and you know instinctively some of the characteristics. and maybe that lets you narrow it down from 4 potential answers to 2. And maybe you're pressed for time, and you decide, I'll push my luck. I know it's one of these 2, and I think it's more likely to be this particular case. So you may want to use that technique from time to time if discretion seems to be the better part of valor.